I've got two formulas up on the board here. This is the formula for compound interest that we worked out in the last video. And this is a new one. This is for interest compounded continuously. So we discussed the fact that the bigger n is, the more times you compound the interest per year, the better the result is, at least if we're talking in terms of investment. Obviously, the worse it is in terms of debt. Okay? And so we might say, if we have an investment, let's not compound interest every month. Let's do it every day. Let's do it every hour, every minute, every second. Okay, well, if we try to do it continuously, we're trying to mimic the natural world. Now, I mentioned, this is going to be an example of decay rather than growth, but with radioactive material, that decays at an exponential rate. Now, the natural world doesn't stop periodically and say, how much radioactive stuff do we have, so that they can assess how much radioactive stuff should decay in the next second. Okay? No, they're just continually adjusting. There's no stopping to calculate it. It's just an ongoing process. Now, it's difficult to do that physically, but we can figure out how to do it mathematically. So this is mathematically how we mimic the natural world, so that we don't stop and assess periodically, but we're just continuously reassessing the process. Now, you'll notice this number E shows up. I mentioned that E shows up in the natural world, so it makes sense that when the financial world is trying to mimic the natural world, we see that number E. Okay. We don't have the tools at this point to fully explain why this is what we get, essentially as we let n go to infinity. But I can do a pseudo explanation. So I'm going to start with A equals P times 1 plus R over N to the NT. And I'm just going to do a change of variables. I'm going to let X represent N over R. Okay. So it's the reciprocal of this interest rate per compounding period. And I'm going to try to introduce X's and get rid of the N's. I'm not going to get rid of the R's, but I can get this in terms of X instead of N. Okay. So if I do that, this would be P times 1 plus X is the reciprocal of this. So this is the reciprocal of X. And then we're raising this to the NT. Well, notice N would be X times R. So I can say we're raising this to the XRT. Now, right now, that gives us a product in that exponent position. That corresponds to a power to a power. I can say that's P times 1 plus 1 over X to the X to the RT. Okay, so easier to see, I think, going from here to here. If I have a power to a power, I would just multiply the powers to get X times R times T. Okay. Now, notice, as n goes to infinity, X would also go to infinity, because R is just going to be a fixed number. Okay. And as X goes to infinity, 1 plus 1 over X to the X goes to E. Now, to prove that, we need calculus. That's a result I have to just give you. Okay, so that's why we don't have the tools to do a full explanation of why when we let n go to infinity, we get this formula. But at least I can get you part of the way. We can manipulate this formula to get it to be this, and then we just have to accept, from those who know calculus, that as x goes to infinity, this number approaches e. Okay, and so that gives us our formula for interest compounded continuously. So let's just calculate if I were using this formula in my example where P was $100 and R was 0.10 and T was 5. Let's just see what our investment would be worth if we compounded our interest continuously. In that case, we'd have A is 100 times E to the R times T would become just 0.5. Okay. Now, your calculator should have a key somewhere for E. You may have to search to find it. It's at different places on different calculators. If you have any trouble figuring out what your calculator looks like, not a problem, let me know. Okay, you can take a picture of your calculator and I can say it's the third key from the top on the second column or whatever. Or we could have a Zoom session and you could show me a picture of your calculator. I'm happy to work with you in figuring it out. Okay. All right, so let's see. We would take 100 times e to the 0.5, and I'm getting $164.87. And if you remember, that's a little bit more than what we got when we calculated what we'd have if we worked with it monthly. Okay. All right, so interest is a major application of exponential functions. I will expect you to know the formulas for interest. We've spent a good bit of time deriving them to try to understand why they work. So I feel perfectly fine saying you should know them because I don't want you to memorize them. I want you to understand them. That's why we spent the time trying to derive them. I can't force you to understand them, but I can force you to be responsible for knowing them. I think it's easier if you understand where they come from and do a little bit of a combination. Don't ban memorization. Yes, memorize this formula, but don't just memorize it blindly. Memorize it by thinking about what the individual parts mean for both of these. Also, you should know the formula for simple interest. There are a lot of other applications. Populations grow at an exponential rate. Radiation decays at an exponential rate. All sorts of applications. You will see a number of those in the homework. For those, the formulas are given in the homework problem. You are responsible for being able to do those homework problems, but just like the homework gives you the formulas, I would give you the formulas on an exam or quiz. So I'm not expecting you to memorize the formulas for population change or exponential decay. I am expecting you to know the ones for interest because we spent the time deriving them. And make sure you do the other homework so that if you're given a new formula, you can interpret it. You know, you might be given something like this and then told in words what P, R, N, and T, and A stand for, and then you've got to interpret that from the question what numbers you're going to be plugging in. So you are responsible for that, but you're not responsible for knowing the formulas for the other applications, just being able to use them when they're given to you.